Hello there again. Now we're going to start part 2 of the radar equation lecture, which is the second lecture, which is part of the Introduction to Radar Systems course. First, we're going to, just for a moment, recapitulate the last view graph from the first part of the lecture. There, we were looking at scaling the search radar equation. Here was the search radar equation. We cast it algebraically into a form where we had the average power equal to all of the other parameters. We noted that the power required is independent of wavelength. It's a very strong function of the range, and it's a linear function of everything else. By a strong function of the range, you can see this r to the fourth power. Okay. Now, what does that mean? Now, let's say, for instance, we have a radar that will work and perform its search at 1,000 kilometers range. What do we have to do to modify that radar to work at 2,000 kilometers range? Well, we have to increase the range by 3 dB. What do we have to do to get there? We can increase the power by 12 dB or 16 times. The diameter by 6 dB, or the area by 12 dB 16 times, by increasing equivalently the scan time of the radar, decreasing the solid angle that the radar looks at, or by increasing the cross-section that we're able to see. In other words, we'll be able to only see targets that are 16 times bigger. Or in a combination of those factors we can put together, redesigning of the radar. So you have to do quite a bit to double your range. All the other things we can trade off one for another. That's as much as to say, if we'd like to see a target half the size, we double the power. If we want the antenna to be half the size, we'd have to double the power. It isn't that strong function that the r to the fourth carries with it, that strong influence. Now let's move on to today's part. First, we're going to start off by looking at 5 different radars. These are all radars that are used for civilian purposes in the United States, so it's very easy to talk about their parameters and their missions and what they do. And here we have a graph plotting as these dots are for the 5 different radars, the average power versus the equivalent antenna diameter of the radar. By equivalent, I mean if the antenna was circular in nature, its size was circular in geometry, what would be the diameter of that circle? Some of these radars, as you can see here, this airport surveillance radar, it's more rectangular. Paraboloid is a nice way to describe it. Rectangular surface. But if the surface was circular, what would be the equivalent diameter? And over here we plot the average power. And we're looking at the search radar performance. Now, first let's look at the airport surveillance radar. Now, this is an airport surveillance radar, an ASR-9. With the FAA is built by the FAA, for the FAA, I should say, by Northrop Grumman, this one is. And these are used at all the major airports to detect aircraft and track aircraft within about 50 or 60 miles of the terminal area of that airport. There's enough of these radars, hundreds, so that they have overlapping coverage over the entire United States, pretty much. Okay. These radars also, you can see another antenna above here, and that's for the beacon tracking. The radar is a non-cooperative sensor, you understand, and whether the target wants to be detected or not, if it has a reasonable cross-section, you can illuminate it, get a backscatter, and detect it. With this beacon system, which operates in tandem, in parallel with the skin tracking radar, so-called, a signal is sent out at L-band, 23 centimeters, and is sent out to the aircraft, where the aircraft have a receiver transponder on it, where it listens constantly, the receiver on the aircraft does, and when it sends a message out, it's literally a coded message saying, "Hey, I'm a beacon system, tell me where you are, and who you are, and what your altitude is." Then, after receiving that signal, the beacon system will send back a signal, and on it will be coded a message with the altitude's height, with the aircraft's height and identification number. And this is obviously an ideal system, but many times on small aircraft, sometimes their beacon transponders in private aircraft don't work. The big commercial aircraft have redundancy for this. But both systems are employed for safety for the FAA, and both are used. Now you see where that radar fits on this average power, equivalent diameter curve. It's got an average power of about a kilowatt, but it's got a peak power actually of about a megawatt. So it's got about a 1,000th is the duty cycle of that radar. It transmits its pulses about every millisecond. And its equivalent diameter is a couple of meters, in the order of a meter or two. Okay, now let's move on to another radar. This is one that's located at most major airports, and most of the time it's located on top of the air traffic control tower, where air traffic controllers visually look at what's going on at the terminal. So it's several hundred feet tall. It operates in the so-called KU band. It's the lower portion of the microwave band, a frequency a little under approximately 2 centimeters, centimeter and a half. It's 16.5 gigahertz approximately. And inside this white pancake-looking radome, a radome is an enclosure that the radar antennas are put in to protect it from the elements, and the radomes are made of a material that the microwave radiation will go through with very little loss in power. And it's rotating around at 60 revolutions per minute. Its function is to look out along the runway and see taxiing aircraft, so that the air traffic controllers who are guiding the aircraft that have just landed and are about to take off, to make sure that one isn't going to crash into the other. And also to keep an eye on vehicular traffic that is around the airport to make sure they don't get in the way. And generally the airport's ground environment is safe and secure. Okay? These are very high resolution radars, and they operate. Here we see its location. It's got a fair-sized antenna, but it's got very, very low power because it only needs to see out 7 kilometers or so. You know, about the distance of a runway and a little more, so to speak. Okay. Next we have another class of radar, air route surveillance radars. And here we see it. That's got a lot more average power, and it's got quite reasonable size. And here's there are quite a few of these located around the periphery of the country, particularly, and they look out about 200 miles. When there were fewer terminal radars, they would fill in gaps in the coverage where there weren't airports that had the requirements for an actual air traffic control radar. They're generally for keeping track of the aircraft that are at high altitudes, along the coastal areas, and they're operated jointly with the Air Force, and to do air surveillance to see what aircraft are coming in. You can imagine there's a large corridor of aircraft coming in from Europe into the Boston, Washington, New York area, and there's another corridor of aircraft coming from Hawaii, from the West Coast to LA and San Francisco, and they keep track of these aircraft that are coming in from foreign locations coming into the United States and keeping border, understanding that these aircraft are doing all the right things from an air traffic control point of view and an air defense point of view also. Okay. Next we have the so-called NEXTRAD. That means it's an acronym for Next Generation Weather Radar. Its nomenclature is WSR-88D, and we see it over here. And we see of all the radars, it has the most, pretty close to the most average power. It's right up there with the AR-SR4, and it's got a pretty large antenna diameter. Now, its job is to look at the weather conditions all over the country. There are just, the entire country is plastered with these radars, and anytime you look at your local weather forecast, you're looking at one of these NEXTRAD radars. They operate at S-band. S-band's a frequency that quite readily sees precipitation and echoes from weather. And these radars have characteristics which we'll talk about later that allow them to measure the Doppler velocity of the targets they see. And their target is the rain and precipitation, that diffuse. It's a diffuse, windborne a target. And to characterize not only its radial velocity by measuring the Doppler shift of the rain cloud echoes from the carrier frequency that was transmitted, but also measure the radar reflectivity, which we'll talk about intensity. And with sophisticated processing with these radars, they can tell all sorts of things. Is there a tornado front coming? They can deal with predictive issues with the weather so that the weather forecasters can put these data into their models and predict where the weather's going to be in the next 4 and 8 hours. But as you remember, when you look at the weather forecasts, they show you a time history of the last several hours or hour or so of how a weather front has been moving into your local geographic area. And they're updated every few minutes. This is the beam, the dish inside this is a parabola. It's a very fine beam, and it scans back and forth around very slowly and carefully so that it's measuring the weather in your area very precisely. Okay. Next is a specialized weather radar that's just located near airports that tend to have turbulent weather, tend to have a phenomenon called wind shear. And this wind shear, where can cause a meteorological phenomena called microbursts. This is particularly dangerous when aircraft are landing or taking off. And the characteristic when there is a wind shear in the area is, think of a circular area where the wind is coming up and then going down. At one side, as you're coming in, it's going up, and then the other, the wind has a downward velocity. Now, when the pilots would be coming in for a landing, they sense this weather pushing the aircraft up, and they want to stay on the appropriate glide slope. So what they do is they push the aircraft to compensate it with the elevation equipment on the wings, the gear on the wings, so that the aircraft will go down faster. But unfortunately, when they get on the other side of the microburst, there's a flip-in sign, and the significant force pushes the aircraft further down. This has led to, that reinforces the already pushing down of the aircraft that they were trying to compensate in the other direction to balance, and pushes the aircraft literally right into the ground. And this phenomenon, before these terminal Doppler weather radars were developed and employed, caused a number of significant crashes with a lot of loss of life. And because of that, these have been employed, and now the air traffic controllers can see that there's hazardous weather. The systems have a automatic mechanism for spotting it and can ring a bell and say, hey, watch out there, there's some microbursts. Anyway, and then they can go over and say, hey, don't use that runway, let's shift to another runway because there's a microburst over in the area of this runway. And these are deployed in the country and do their job. Since they don't have to see out as far, they're also looking at weather of the same size and cross-section. There's less need for them to see further out in range because they're dealing with issues closer to the airport. And they can have a detection range that's significantly less. Okay. Now, before I go on, I just want to point out that in this graph, all these curves have been normalized so that they are searching 1 steradian of solid angle in 10 seconds and looking at 1 square meter target with a signal-to-noise ratio of 15 dB, the losses of about 10 dB, and that system temperature of about 500 degrees. But these parameters aren't the required requirements in terms of detection for these different radars, but it just shows you the different relative powers. I just note that if you were building a radar to see up in space, satellites, on the power antenna curve, it would be way up here. And if you're a policeman with a handheld police radar that's trying to catch speeders, you're only talking about a quarter of a mile or so with a relatively large cross-section target of an automobile, and you'd be way down here. So radars fall all along these lines. And remember, these scales are logarithmic and go from an average power of 1 watt up to 100,000 watts, and diameters from 1/10 of a meter all the way up to 100 meters. So radars of all different kinds fill up this entire region. And I just wanted to highlight 5 different radars that are used with civilian applications and what their relative power and how they work. Okay, now let's go on and go back to that issue of radar losses. Now, I said that the radar loss terms in the radar equation are the humanity of the radar. And that is to say, they're the lack of idealism in terms of how you get power from the transmitter. And I've divided it up, you can see here, into the transmit chain and the receive chain. But let's just think about the transmit chain, and that would be from the transmitter till we get to the target. And in order to do that, you have to go through waveguide, you have to go through radome, all sorts of things have to be taken into account. And when one is designing a radar, you have to take into account the losses as the transmit beam goes through the radome, if it has a radome, the waveguide feeds and the waveguide themselves, the circulator, which is that switch. There are filters that you can put in the transmit chain. There's a joint if you have an antenna that rotates mechanically, like the airport surveillance radars, the ASRs and the ARSRs. There's a joint where the microwave energy goes up and it has to go up through and then to the feed. There are losses in that rotary joint. There's the efficiency of how efficiently the energy goes out into the transmitter. And when the target is illuminating, the radar is illuminating the target, is the radar pointing directly at the target or a little off? If it's a mechanically rotating antenna, maybe the target's a little off and it's not on the peak of the gain pattern of the antenna. And there are a number of other losses, a loss through the atmosphere and I'd like to just point out also the issue of field degradation. When one builds a radar and builds it as a laboratory instrument, it will work to a certain level. Then after a radar is out in the field, the transmit doesn't quite generate exactly the power that it was specified to. It generates just a little bit less. And one by one, over time, all of these different pieces of humanity of the radar, the losses increase. And so in time, when you take a radar out and operate it in the field, and many radars are transportable, you take them, you can put them in an airplane, take them apart into subsystems, and then set them up. They just don't quite operate as well. They're very complex entities. They don't operate as well as they would in a laboratory environment. So usually sensible radar engineers, when they design a radar, they put into it a certain field degradation, because after a while you want the radar to work 5 and 8 and 10 years after you build it. Those are just the losses on the transmit side. And we have a whole series of losses on the receive side also that deal with the signal coming back from the target all the way back to the receiver. And they're pretty much, a lot of them, the same, but after you get back to the receiver, there are losses in the processing that take place. Now notice I've said loss, 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 loss. I haven't said plus, 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 plus anywhere. And that's one of the key things about this whole issue. The radar you build is the best you can hope for usually. And so you really have to be very careful, because if just each one of these parameters were off by 1/10 of a dB or 2/10 of a dB, there are probably 25 parameters here, then the whole radar's signal-to-noise ratio would be down 5 dB, and the detection range of the radar would be very severely degraded. So when people are designing radars, they have to be very keen and very careful about putting in the appropriate and exact quantities that are realistically expected from these. Depending upon the mission of the radar and the type of the radar, overall, the total of the transmit and receive losses can vary from 5 to 15 dB. And 10 dB isn't at all an unrealistic number for the total of these losses, particularly when you consider that how many of them there are. Okay. Now I'd just like to go over a number of different losses in particular and talk about them to give you a little more of a physical intuition of some of the main losses. One I talked about earlier, and this is particularly in scanning antennas that mechanically scan, the radar return is modulated by the antenna as it moves across. The gain of the antenna is higher. It they detect it as you see the target, and the target moves into your beam as you move the antenna over the azimuth where the target is located. Then your signal-to-noise ratio will increase and decrease, consistent with the antenna pattern as you go into the main lobe of the beam up to the peak and down. Now, so therefore the return is going to be modulated by that antenna beam. This beam shape loss can be in and of itself, just one loss, can be 2 to 4 dB. Okay? There's a scanning antenna loss for phased array radars where when you go and point the antenna in the direction where you think the target is, it's not quite there. So you can be you can be not where you expect to be. Excuse me. This scanning antenna loss is for phased array radars. When you build a phased array radar, and we'll get to what they are later, they're an antenna that has a beam shape when you're pointing perpendicular to the phased array face, and the beam shape broadens as you go off the antenna shape face. That can be quite significant. So if you've scanned 20 degrees off the perpendicular to the face of the antenna and you're detecting the target, there's a significant loss in gain of the antenna, and that is this scanning antenna loss. This is what we call so-called plumbing losses. And these are the losses as we transmit the energy up and down the waveguide and transmit and receive in the rotary joints and circulators. These can be 2 or 3 dB. It'll depend a lot on your frequencies. At the higher frequencies, like at X band, 3 centimeters, the loss per 100 feet of waveguide is significantly more than at lower frequencies. And then there's a lot of signal processing losses. Signal processing can do great things to help you see small targets in the presence of clutter. But as we do that processing, there's a loss when we do the A to D quantization, when we apply adaptive thresholding systems, so-called constant false alarm thresholding. You'll learn what these are later. But I just want, and range and straddling loss and range and Doppler weighting losses. We'll talk about them somewhat later. But these losses, there's a significant number of losses associated with signal processing that can be a dB or 2. And we can't forget the loss in the atmosphere, and that's a two-way loss. And as you'll see in the next lecture on propagation, the attenuation loss at higher frequencies can be quite significant. When we do integration, if you non-coherently integrate pulses, that most of the time that's not as efficient as coherent integration, and you can have a loss there. And then I went into the field degradation loss. A reasonable loss for that to put in is I usually put in 3 dB when I'm doing radar design issues. You can have water in the waveguide. It can leak in. The receiver's noise figure can degrade over time, and poorly tuned or weak transmitter tubes. These are things that just happen in time. And of course, some of these you can fix with periodic maintenance, but between the periodic maintenance, some of these issues can occur and the radars don't quite perform up to standard.